Let's say you've got an object that is a conductor, not an insulator. Everything we're going to talk about over the next 10 to 15 meters is for a conductor because the charges don't move as freely around on an insulator. If we look at charge distribution on an insulator, all bets are off because those charges don't move around very easily. If we have a conductor that has, for whatever reason, excess charge on it, maybe it's been struck by lightning, maybe it's just been touched against something that's already charged, it will end up with excess charge. What does the distribution of charge look like in or on that conductor? Where do the extra charges go? Well, it ends up being pretty predictable, actually. Why? Well, because these charges always want to reach a state of static equilibrium. Static means not moving. Equilibrium means equal forces, balanced forces. So these charges, these electrons, these excess electrons, they push each other away. They repel each other, until at some point, the force of repulsion of this electron on that electron is equal to the force of repulsion on these other electrons as well. The forces end up balancing, and they end up becoming in a state of equilibrium, balanced forces. They stop moving. We're in static equilibrium. But what does the distribution look like? What does the spacing of the charges look like as a result of that state of static equilibrium being formed? We'll look at a few different shapes here. The first one is a solid conducting sphere. We talked about this a little bit yesterday, but we'll spend a little bit more time on it today. It's like a ball. It's like a marble, except it's made out of metal, some kind of steel or copper or something that's a conductor. And for whatever reason, it's gained all these excess charges. Maybe it's got 1,000,000 protons. In this diagram, if it has 1,000,000 protons, it's got 1,000,003 electrons, 3 excess electrons. It's not the 1,000,000 electrons that we're concerned about, it's the 3 extras that we're concerned about. They're going to repel each other. If we label these 1, 2, and 3, 1 is going to be pushed away from number 2. It's also going to be pushed away from number 3, giving us a net force acting on number 1 that looks something like this. 2 is going to be pushed away from number 1, also pushed away from number 3. The net force on number 2 looks something like this. 3 is pushed away from number 2. 3 is also pushed away from number 1, giving us a net force on number 3 that looks like this. The net force on all of these excess charges points outward. That means all of the excess charges will be pushed to the outer surface of the conductor. That always happens, no matter what the shape. The excess charges get pushed to the outer surface. You know, to tell me why they stop there? Why don't they keep going? Like, why don't they move into the air? Remember we said at the very beginning of this today, we said that, are you going to give me an answer there? No? We said that the analysis that we do here doesn't really apply to insulators because the electrons don't move very freely in insulators. When they move to the outer surface, they stop because they don't want to move into the air, which is an insulator. So they stop at the edge of the conductor, on the outside surface of the conductor. What does the distribution look like in the end? Well, these charges go to the outer surface. And they are evenly spaced. There's an even distribution, a uniform distribution on the outer surface. So they're equidistant apart from one another. Excess charges will always go to the outer surface, no matter what the shape. They will not always be evenly spaced, but if it's a nice uniform shape, like a solid conducting sphere, they will be evenly spaced. Now, the second diagram that we see, and we saw this yesterday as well, involves, again, a nice uniform shape, flat plate. It's got excess charge on it for whatever reason. 1,000,000 protons, 1,000,003 electrons. 3 excess electrons. Charge number 2 is going to be pushed to the right because of number 1. Charge number 2 is going to be pushed to the left because of number 3. Why is 1, 2 bigger? Because it's closer to charge number 1 than it is number 3. What's going to happen as a result of 1, 2 being bigger? Charge number 2 is going to move to the Which way is the bigger force? 3-2 or 1-2? 3-2. So which way is it going to move?
Right.
To the right. It's going to move in the direction of the bigger force, right? So as it moves to the right in the direction of the bigger force, what happens to the value of F12? As it moves further away from number 1, F12 becomes smaller, right? What happens to 3-2 as it gets closer to number 3? F32 becomes, see? Bigger, right? So this is F12, this hand is F12, this hand is F32. F12 starts off quite a bit bigger than F32. As it moves to the right, F12 goes down. F32 goes up. You can see my hands here in just a moment. The two forces are going to be equal to each other right now, right? What happens when they're equal to each other? Things stop moving around. It's in a state of static equilibrium. The forces are balanced. Where does that occur? When are these two forces equal to each other? When this charge is in the middle. Once again, the charges have gone to the outer surface of the material, and once again, they're evenly spaced. Why? Because it's a nice uniform shape. If you get a uniform shape, the charges go to the outer surface and are evenly spaced. Now, that is as opposed to an irregularly shaped object. And what I mean by an irregularly shaped object is more of a pointy object, where you have a sharper point. I'm going to cover up part of this because I want you to see the steps in determining what the distribution looks like, not just the final product. We're going to label these charges again 1, 2, and 3. We're not even going to pay attention to the fourth one here. We could, but it's not necessary for us to analyze the fourth one to see what happens. Charge 1, charge 2, charge 3. There's a million protons, there's 1,000,003 electrons, 3 excess electrons now. Charge number 2 experiences two forces. It experiences a force to the right caused by number 1. Do you see that? It's pushed away from number 1 as a result of repulsion. Charge number 2 is also pushed away from number 3. It's repelled by number 3 this way. You see that? Right? Pushed up and to the right away from number 1, pushed up and to the left away from number 3. Now I'm going to break F32 into a couple of components. I'll call this Fx, and I'll call this Fy. Fx is the x component of F32, Fy is the y component of F32. What does Fy do? What is the effect of Fy, the y component of F32? What does it do to charge 2? Remember we said a little while ago that it doesn't matter what the shape is, all excess charges will go to the outer surface of a material. Why do they go to the outer surface here? Well, because Fy pushes charge 2 to the outside. Look, it's perpendicular to the surface here. It pushes it to the outside. Fy is what makes the charges go to the outer surface of the material here. Now we're looking at F12 and Fx. Which one's bigger? The x component of 3,2 or F12? F12. So which way is charge 2 going to move as a result of F12 being bigger? Let's call it left and right, even though it's kind of diagonal there, right? You see what I mean when I say left and right, though? If F12 is to the right and Fx is to the left, which way is the charge going to move? You said it, Jacob. It's going to move to the right. Okay, as it moves to the right towards the pointy part here, towards the tip, what happens to the value of F12? As it gets further away from charge 1, F12 goes down, right? At some point, Fx and F12 will balance. But it's not going to be where they are right now. It's going to be when that charge number 2 gets closer to the tip. So what does the distribution end up looking like? Look at diagram C here now. we've reached a point of static equilibrium in diagram C. The charges have gone to the outer surface, but they're not evenly spaced. There's a higher concentration of charges at the tip. Charges become more concentrated at the pointy parts, or at the more pointy parts. They go to the outer surface, and if it's a nice uniform shape, they're evenly spaced. If it's a non-uniform shape, we get a more higher concentration at the pointy parts. When you were a little kid, say 4 years old, intuitively you knew this. You learned this through experimentation. That's how you learn everything when you're a kid. You don't realize you're experimenting, but that's exactly what you're doing when you're a little kid, is you do experiments. When you're a little kid, you learned by yourself that when you wanted to shock somebody, you would walk across the carpet and you would touch somebody with the tip of your finger. You wouldn't rub across the carpet with your feet and then go up against somebody and touch them with the side of your arm. You would touch them with your fingertip, because intuitively you knew that pointy things like your finger built up more charge than flat things or uniform things like your arm, right? You knew that. You might not have known exactly why that was the case. You probably didn't. Okay, but you at some level knew that pointy things built up more charge than flat things. So that's why. Because in order to reach a state of static equilibrium, the charges have to be more concentrated at the pointy part than they do at the flat point, or the flat part, right? Finally, we have a hollow conducting object, which is real similar to a solid conducting object, except it's hollow. So this is a sphere, or really, it doesn't really matter what the shape, but in this case, a sphere that has nothing inside. I'm not going to describe to you why the electrons go to the outer surface, because we already know that from the solid conducting sphere. They're going to be, in this case, evenly distributed because it's a nice uniform surface. That means the electric field is going to point this way, right, towards the negatives. I want to focus on the electric field inside, though. The electric field at this spot right here. The electric field at this spot points toward charge number 1. It points toward charge number 2. It points toward charge number 3. If I did a vector analysis on these fields, and I'm not going to do that because I don't have any numbers with these, but if I did, if I had numbers and angles and I did a vector analysis, what do you think the x components would add up to be? What do you think the y components of these fields would add up to be? 0. The net electric field inside is equal to 0. This is what we call a Faraday cage. When you have a conducting container, we'll say, the net electric field inside that conducting container is 0. That means it's perfectly safe. The video that I just showed you a minute ago with the airplane, the 747 being struck by lightning, those people inside the airplane probably never even knew they were struck by lightning. The pilot probably knew, but the passengers probably never even knew. Why? Well, because the net electric field inside was 0. They wouldn't have felt the hair on their arms stand up because there was no electric field. They wouldn't have been electrocuted because the net electric field inside a metal Faraday cage, i.e. the 747 airplane, was 0. That's why a car is a safe place to be in a lightning storm, right? Everybody thinks it's because of the rubber tires. You think if the electrons can make it from a cloud a few kilometers up in the sky to the car, through the air, you don't think they can make it through a half an inch of rubber? Of course they can. The rubber tires have nothing to do with the safety of a car in a lightning storm. The car is a Faraday cage. And when lightning strikes the car, the net electric field inside the car is 0, which means it's perfectly safe. It might be scary if your car was to get struck by lightning, because if you're in a car, you definitely know it, but it wouldn't hurt you, at least not physically.